All right, stats, this is our third and final part of chapter 12.1 notes. So the one thing that I skipped over in both categories, both in the confidence interval and in the significance test, was the assumptions and conditions, because there are a lot more assumptions and conditions with these than any of the other ones. And the other ones, there were 3. We're now upping that to 5. And the main 5 that you're going to use, they're going to help remind you by using the words liner, kind of like line, we're doing best fit line stuff, or you can think of it as linear if you want and just pretend that the A just means and it is one of the tested categories. So I'm going to run through these. So again, if they give us a computer printout, then they have to provide these graphs for us. You're not going to have to create these from scratch, which is going to make this part a lot easier. So remember that they can show you the original scatter plot. Right? That's just all the x's against y's. They can show you a dual plot. Right? And both of those would be used from doing linear regression, right, on our calculators if we had the raw data. Okay? So those are the main 2 that we're used to seeing. So the first part about liner is the L. And the first thing we're going to do is just look at the scatter plot and see, does it look like it's a linear best fit? And so we can just look at the dots, pretend that the green line is not there, and say, would this look like a best fit line or would it be curved? So it looks like it would be linear, okay? And then the other thing is, so we'd look at the scatter plot, then the other thing is to check there's no pattern or curve in the residual plot. You need to do both, okay? And there is no pattern or curve here, so we qualify for L. So we're good there for L. The next one is I, no shocker, this is the one that we're checking before. If we're doing sampling, we want to make sure that we're not sampling more than 10% of the population, okay? And any reason that they don't tell you any of that information, you can just simply state each observation is independent of the next observation, okay? So there is your set phrase of if they don't give you enough about sampling information, you can just say each observation is independent. If it's coming from an experiment, remember you don't even have to check this one. Okay, so there's our independence. The next part of linear is normality. Okay, now in normality, we want to look at and make sure that, that the best fit line would also follow a normal curve. So one of the ways we do that was we're not saying like, is the best fit of all the scatter plot a normal curve? Like, does it make a bell curve? We're not saying that at all. What we're saying is if I took all of the residuals, would the residuals, when I plot them, make a normal curve? Okay, so this is a new graph that you have not seen before. This is a residual on the x's, and on the y's is just how many there are or a count. So if you had to create this one, you could create it from the residual graph, no problem. Let's go and show you how to do that. But again, they might just give it to you, and that would be lovely as well. If I had to, here's what I'd be looking at. I'd be looking at each dot to figure out what its approximate residual is. So in this first one, the residual is about -5. Okay, so then I would come down here, and at -5, this would be one of my counts. And it looks like they're saying there were 3 of those. Let's go see if we can find the 3 -5s. So if I go across to -5, it looks like there might be another one like here and here maybe. Right? So this would be super tedious to do by scratch. So it's more likely that they would give you this already presented. Okay? And all we're looking at is it is approximately normal. It looks approximately normal. We want to say that, say it's approximately normal, no major skews or outliers. Okay? So this is a new graph. This is residual counts, just as a bar graph, as a histogram. You could even do this one as a stem and leaf plot, right? And just start as a like a -5 would be here. There are 3 of them, something like that. Okay, scratch, but they shouldn't be asking you to do that. The other one is a really tricky one, and I'm going to just show it to you, but I'm going to say we usually do not use this one. Okay, and this is called a normal probability plot. Okay, it's a normal probability plot. So the x is the same x-axis as the other one. It's a residual. But then the y-axis turns into z-scores. And so if you think about this, if I look at where all these dots are kind of horizontally, there's very few here, there's very few dots down here, but in the middle, there's a whole lot more, right? And so if I were to graph that, it would kind of look a bell curve, kind of like that. So what they do is they say, if I take all the z-scores should form a really nice line, a diagonal line that goes through all of those, all right? Again, this takes a really long time to provide. If they provide it and they call it a normal probability plot, all you'd have to say is the normal probability plot appears linear and you're good to go. But again, this would not be one you want to create by scratch. You'd be fine reading it if they show it, but you prefer to say something about a normal probability plot, okay? Creating this on our own is not a fun deal. This is not one that you want to create on your own. All right, probability check. So this is a new step for us, right? Because we'd have to create one of those or we go look for one of those that's been provided. So if this is a computer printout, they got to give us a lot of extra graphs, all right? And then the last one, again, A is going to stand for and. Oh, we're not there yet. E, equal standard deviations. Okay, so for this one, we're going to be looking at the residual plot. This is the same one from our one that we got in the beginning. Okay, exactly same one. And what we're looking for these is about the same spread across all the x's. So again, we want to continue with these tests, so we want to be able to say they pass. So basically what we're looking at is that the spread on the left side of the residual graph is about as wide as the spread on the right side, that we're not seeing any trumpeting or where they kind of go together. So if I look over here, I can see that from high to low, we're right about here. Over here, we're still right about here. So it doesn't really look like that we're changing much, okay, that they're about the same all the way across. If I saw a residual plot that looked like really close here, a little bit larger here, a little bit larger here, right? That's not what we'd want to see. Okay, but as long as it looks relatively scattered, you're okay. You're just going to tell them that the residual plot shows similar variability. Okay, and then A is for and last part is random, and that's our same random from before. We're going to say it's random sample of 200 students or random assignment and experiment where we put them into 2 treatment groups. So those are all the same. So this one takes an awful lot longer. Now imagine if they gave you the original data, you would have to find ways to create all 3 of those big graphs. We already know how to create the first 2, right? But the next one that would be way more difficult is you would have to create this histogram of residuals. And again, it's just for a check to be able to continue to do the mathy part. So it is much more likely they're going to provide you everything, and you just have to say what graph you looked at and what you're looking for. That's where your focus should be. Awesome. All right, that's it. We'll see you later.